give a big hand to Marc Antoine.
Hi, everyone. So my name is Marc Antoine. I work as a field application engineer at Synaptics. And in today's workshops, I will discuss how Synaptics Toolkit can significantly accelerate your AI development for your application. So this platform is really designed to streamline the process from the model creation, then to the deployment, making an easy and fast way for developers to bring AI functionality to the market. So I will cover just 3 topics. So I will just start to do our first introduction of our Astra platform. This is the latest toolkit that we just came out this year, beginning of this year. Then I will do a quick introduction about how you can implement our Synap Toolkit. And then at the end, I will just demonstrate the advantage of using Synap Toolkit in a real application that's doing a heart rate monitor. So just want to briefly just introduce Synaptics. So we are, some leaders in user interface. I think some people know Synaptics for the touchpad and touchscreen. So this is where we start. So it's ready for the sense. So using the user inputs to then interact with the people. And then once you have the information, you need to compute that. So it's why we also develop some process with high performance MPU and MCU to do all this intelligence on the device. And then finally, for your application, you need some connection. So it's why we also have like brand product for Wi-Fi, Zigbee, Bluetooth, or GPS. So this is a bit the history where Synaptics come from the on-device AI. So Synaptics has a long history discovery. Our company, so we had like various implementation of AI across our product line, starting from 2016 to today with this new Astra platform. So we already have some knowledge. It's why then with all of this knowledge, we bring and come to this Astra solution. So, So our Astra new compute platform for IoT is based on 5 fundamental pillars. So we have like all the compute solution. So we have a various NPU and MCU to be used for your application. We try to have like an adaptive AI framework that works with all our chips. So like this, once you develop something for our solution, you don't need to relearn and redo everything from scratch. So our goal is like to make AI works than working with AI. And we try like to have like a unified software experience. This is we have like different solutions to the open source Linux, supporting Android and RTOS also for our solution. And then we try to build a partners ecosystem that help us to then promote our chip for different kind of customers. And finally, we still, as I explained, we have like the wireless connectivity. So the Astra platform is also able just to support our different Wi-Fi, Bluetooth, or BLE chips. Okay, this is the family of the different AI edge processor that we have. We have like some high performance MPU and MCU, and to some connectivity MCU. Here in today's Synaptics is really today I just really focus on our high performance MPU, just to demonstrate how we can use Synaptics for that, Synap tool for that. So this is, just let me briefly introduce our new dev kit that is available now on the market, where we just developed this toolkit for early adopters. Like this, they can already start to develop their solution on our platform, and you just need to buy this toolkit. So what is based on, so we have like the core module with different type of SoC that we have, coming from the high end where we have more AI capabilities to the low end where you need just to have like low power consumption. And then we have like the motherboard, the I/O board, with all the input that you need to use for the chip. Once we have the hardware, you need the software. That's also important. So it's why we developed this open source Linux SDK, really tailored for the IoT market. So we try to have with the same SDK, we support multiple SoC from our own. And then we have also multiple profile. You can do some home automation to some surveillance. All of this stuff can be embedded with the same SDK. We try to have a unified framework. This is just helping developers to fast develop on our platform. We do because we also have optimize wireless and support multiple OS support. And then also we try to have very good documentation. Everything is open source, so you can find all the information on GitHub. With also some sample application that help you then to take your solution on our solution. So I will continue with the Synap Toolkit. So this is just to show you the capability of the Synap. So this toolkit is really designed the core component to do the AI deployment. Okay, so our AI solution addresses the full stack from the model to the compiler. So the framework is just support different type of NPU, GPU, and CPU. And this is really the scope. This is where we're gonna really focus on how to use the Synap to then transpose your model into our platform. Sorry, I got a bit too. So our model optimization is just a simple Docker that you can use that is really Python based and to do the cross compilation for the supported platform. You can import your model from TensorLite, TensorFlow, PyTorch via ONNX, even Caffe and ONNX model. We do the model optimization with the Synap. And also, we provide all the network graph and metadata generated ready for the NPU. So this is just to explain a bit how the framework is done. So we have the Synap Toolkit. Then we have the Synap runtime that is running on the device. And then that's then target which type of NPU you want to target your model that you build. So if I take just this small example, so if we take just a YOLO 5 model, there is the possibility just to take the quantized model that you just built by yourself, and then you just use Synap, and then you can directly launch on the platform, and just to check how is perform for your application. There is also possibility to do some optimization. So we support recotization int8 with mixed precision. We can also apply some pre-processing option from the training. We can also remove some optimal layer. That's if you use this solution that can improve the latency with a better accuracy of over 30%. So I will showcase that in the next slide. So here, this is where you can find all the information about our solution. So everything is on GitHub. The good thing is everything is open source, so you can directly connect there, search for Synaptics Synap, and you can find all the documentation, everything you need then for your development. Let's do some demonstration about how to run model optimization. So we have a partners that is Darwin Edge, that they develop a remote vital detection pipeline. So what they do is they start with some videos, they do some pre-processing from the input frame, then they run some face detection inference, just to decode the phase and extract the bounding box. And then they do just the tile reduction to extract the corner channel from the reduced bounding box. And then they run hard rate detect frequency analysis on the input data, and they do the hard rate phase detection, hard rate detection, and the tracking. So this is really on the video. So what they really need is like having a good phase detector that then can run then the solution. Then they run their algorithm to extract the hard rate. So what we can do is we use just a pre-trained model, a retina phase model, a simple one that we can find on GitHub or whatever you want. You do just a simple conversion. And now I will just show you if we run that on our platform. So doing no optimization. So here we just run it as it is. So here what you can see is, okay, the phase detection is very accurate. The only issue is it's taking, to do the inference, it's taking more than 200 milliseconds. So for an application that is running, I mean, if you want to run a real-time application, you cannot do it because you're going to be screwed and it's going to take forever. So here it's okay because I do post-processing of the video, but in real time, it's not going to work at all. So how can we optimize our model? So it's where comes the quantization. So model quantization can be done really after during the training. So this is the quantization hour training. So this is for the best accuracy. This is applying during the model training with some training in TensorFlow on Python. Or we can do also post-training quantization. This is applying after the training, and this is simplified the model size, reduction, and speed up the inference. So what we develop with Synaptics is using our Synap Toolkit to do the integration. So we have like the direct compilation just to avoid the format conversion by quantizing directly during the model compilation. So what you need to do is just like having a quantized data set, just a representative input of files, the set for the quantization parameter efficiently. And what we try to simplify is instead of having a huge command line to be used, everything is in a meta file. That way you can specify all the conversion that you need for your model. So if I just summary a bit what we're going to do, we have our YAML file with the different input that coming from our model, with the mean and the scale. And what we need from the output is just some dequantized data. And then when we run the quantization, we just specify which type you want to use and where is the path to the data set. So Synap Toolkit will just bring all together and then generate a new .synap file model that can directly then run for your application. So let's see how it improves for our final application. So now, as you can see, we reach now almost 30 frames per second. That's super cool, but we lost a lot in precision. As you see, there's a lot of flickering. So that's mean what the problem is here. What we did is maybe go a bit too far on the quantization. So we lost a lot of imprecision, but we gain in speed. But we have solution. We support int16 quantization. So our NPU have the capability to do either 8-bit or 16-bit quantization. So so the only don't thing for that is we don't just support normal TensorFlow standard model with just 16-bit. It's gonna come in the future. That's still under development. If we compare the performance, if we do 16-bit inference, it's like around 2 to 3 times slower than 8-bit. But if we compare to float 16, it's really much faster. So if we see that on some scenarios the 8-bit quantization is a bit too aggressive, maybe it's a good method to go for the int16. So exactly the same thing. We just change one thing is our data type just to int16. We collapse all the data sets and run it. So, oh. So here, as you can see, now we are around 23 frames per second. We see that we have a lot of very good precision. And now we see that the inference time to do the face recognition is around 13 milliseconds. So that's pretty good, but can we be a bit more aggressive? It's where we come with the mixed quantization. So we have like the possibility to do either some layers in int8 or some layer in int16. So this is really where you need to find the balance between the precision and the speed. So what we see is just we need to really select the best 16-bit quantization are the one with where we see the more quantization error. So how we do that is we just use the KL divergence to then measure the error of that. So we have like in Synap the functionality just to also generate the entropy for the different layer and just to give us what is the error for that part of the model. So what we see is more you diverge, so it's where you're closer to one, indicate there is a lot of quantization errors. The best approach is use the backbone, so the beginning of your model in 8-bit, and then when we start to have like, just to improve the accuracy at the end with the 16-bit, this is really when we have like critical output and where we need more precision. Our observation is generally the final layer is where you need more precision and where there is the most of the errors. And then, so this is why it's really critical just to move to int16 at the end of the model, and then to just do this prioritization for those steps. So what I did is I just opened my model with Neutron and just check. So here, just zoom on some part where we see with the entropy that we get. It's from there we start to have like some divergence. So what I can choose is starting from this node on the model, I can do then int16 quantization. So this is what we do. We still have the same thing. The only difference is we say, okay, starting from here, you do int8 quantization, and then starting from that point of the layer, you do int16. We keep the same data set, and then we can run on our application. So as you can see, okay, there's still a bit of some flickering. We still have like some work to do. But we now a bit higher, that's 20 frames per second. And the inference take only 8 milliseconds to do the analysis. So if we compare to just a quick resume of what we get. So we're starting from a float 16, where it took like more than 200 milliseconds to do the inference, where we see that we are a bit too aggressive, going down to 5 milliseconds. And then once we go to int16, we have around 13 milliseconds. And if we want to try, maybe we can change the layer where we want to do the optimization. And then if we do the mix, we arrive around 8 milliseconds. So starting for our application, we start like with a total time just to do the analysis from 30 milliseconds, and we divide by 10 the computation with the same model. So this is really where we try to do our optimization. So thank you for listening. Just let me know if you have any questions.
Thank you so much indeed. Now, does anyone have any questions For Marc Antoine, just put your hands up if you have anything that wasn't clear, or was it all super clear? Here we go. Let me come with the microphone.
Hey, just out of interest, with the use case that you were showing,
Yeah.
there was a heart rate
Yes, exactly.
data being shown. I was just wondering, were you able to cross-reference that with a like blood pressure or heart
That's
rate?
the next step. So
Okay.
currently what we did is with our partners, we just start with the heart rate detection. And the goal is to reuse some similar techniques to then do the blood pressure, the O2 analysis, for example, all vital signs from the video. That's really the goal. So there is clinical, they're now doing some, with the University of, with the Hospital University of Lausanne, they start to do some trial clinic and just to collect more data to then improve also the model and the solution.
Thank you.
Thank you. Was there anyone else? Right over here.
Sorry, a simple question. What is the minimum resolution of the camera to get that result?
As you see, we don't need a very huge resolution because we do some pre-processing. So the model itself needs just 14 by 480 by 360. So this is the bare minimum that we need. Maybe just a bit higher to get the ROM, but this is where we start to get to the face detection. So yeah, it's very, very low.
Fantastic. Thank you very much. Good. If there are no more questions, you can always nobble Marc Antoine after he's finished. And you have your QR code here if you've all probably done it for your CPD accreditation. And if we can all put our hands together for Marc Antoine. Thank you very much.